in the last couple of lectures we were discussing state space search, and if you remember in the initial introduction that I gave on search, we said that there are three different paradigms for problem solving using search broadly. One was state space search, of which there are a few topics which are left, we will cover that up later. The second topic is problem reduction search, and under problem reduction search we will look at two kinds of graph search, namely Andor graphs and game trees. Andor graphs are a kind of structure which we will study, and it has several different applications, though people do not always refer to them as Andor graph search, but the underlying philosophy is the same. And then we will look at game trees, which is the backbone of game playing programs and for programs which optimize in the presence of an adversary. So, games are situations where you have adversaries and there is some criterion that you have to optimize, and in the presence of the adversary you have to do that optimization. So, problem reduction search can be broadly defined as planning how best to solve a problem that can be recursively decomposed into subproblems in multiple ways. So, we can solve the same problem by decomposition. There are more than one decompositions of the same problem, and we have to decide which is the best way to decompose the problem, so that the total solution cost, quality of solution or the effort of searching is minimized. So, to start with, let us consider the matrix multiplication problem, where you are given a set of matrices A1 through AN, and we have to find out the product of them. So, we have to find out A1, A2 to N, right. Now, we can do it in several ways. For example, we can first multiply A1 A2, with that product we can multiply A3, right. With that product we can multiply A4. This is one way of doing it. Another way could be that we first multiply A1 A2, then we multiply A3 A4, right, then we multiply A5 A6, then A7 A8 in this way, and then we multiply these two, multiply the product of A1 A2 with the product of A3 A4 and the product of these two, and then finally in the final step we multiply the product of these, right. So, it means that if you look at it bottom up, then here are our matrices A1, and so on, and one way of multiplying is by taking these two and these two and these two, right. So, this if we look at it from the other direction, so the problem of multiplying it A1 A2 A3 A4 can be thought of as multiplying A1 A2 and then A3 A4 and then this, right. An alternative way of doing this would be to have right, and A1 A2 A3 can be done with A1 A2 A3. So, this is another decomposition, right. So, this way is one decomposition, this way is another decomposition. These arcs that I draw here indicate that both of these has to be done, right. So, you cannot do one of them. So, for example, when I have an AND here, it means that you have to solve this sub problem of finding out A1 A2 and this sub problem of multiplying A3 A4, and then you can solve this. So, once you have solved this one and once you have solved this one, then you can solve this, right. Now, as you can see that there is a cost associated with each of these multiplications. So, if I have, if A1 is n cross n, if A1 is n cross m and A2 is m cross k, then the complexity of finding the product A1 A2 is what? N into m into k, right? And what is the size of this matrix? It becomes n cross k. So, when I take this n cross k matrix and then I multiply it with another k cross z matrix, then the cost will become n cross k cross z, right. Now, you can easily see that these products which will all have different costs. So, depending on the decomposition, the total number of operations that you have to do for the matrix multiplication will vary. So, one problem is to determine what is the best way to multiply a given set of matrices, and there are different kinds of solutions to this problem. For example, you may have studied dynamic programming solutions to this problem. It is not difficult to create a dynamic programming formulation for this problem. We will see how to cast these general problems into an Andor graph search framework, and we will study one algorithm for solving them. Coming to other examples of problem reduction search, there are several planning problems which get decomposed into sub problems, and there are many ways of decomposing it. Are you familiar with the Tower of Hanoi problem? Okay. The problem is like this, that you have 3 pegs and one of them contains a set of disks. Now, these are disks which have been put in from the top. So, these are round disks which have been inserted. So, they have a hole in between. So, you can put them on this cake. Now, what we have to do is to transfer all of these pegs, all of these disks from A to C using B as an intermediate, but the constraint is that I cannot at any point of time put a larger disk on top of a smaller one. So, during the entire transfer I can move one disk at a time. I am not allowed to move more than one disk at a time. So, the constraints are one disk at a time, right, and the second constraint is that smaller disk can never sit on a, rather it is the other way around, a larger disk cannot sit on a, can never sit on a smaller one, right. So, with that restriction, with these two restrictions, we have to transfer the set of disks from A to C. So, there is a very neat recursive solution to this, that says that use the algorithm. Suppose we have an algorithm, say P. So, use the algorithm P to transfer the top n minus 1 disks, from A to B, right. Now, when you are moving these top n minus 1 disks, the largest disk is here, it remains here. So, it is a sub problem of shifting the smaller n minus 1 to the second disk. Once you have solved this sub problem, then you transfer the largest disk from A to C. There is no problem in doing this, because at that time C is empty, and then recursively again transfer the n minus 1 disks that were in B to C, right. So, what we have here is, suppose we say that the initial problem was to transfer n disks from A to C. Then we are basically decomposing this into 3 sub problems that transfer the top n minus 1 disks from A to B, then transfer the largest disk, right, from A to C, and then transfer the n minus 1 disks that were moved to B. So, they are now moved to B to C. So, we have to solve all these problems in order to solve the tower of Hanoi. So, this is one kind of decomposition of the problem. There can be many other ways of decomposing the problem, right. Once you have chosen a decomposition, the solving procedure is standard, but the objective here is to determine that which of these methodologies of decomposing the problem works best for a given problem. Then there are blocks world problems in planning. We will discuss this later when we talk about planning problems, and also theorem proving, where in order to prove something we will see that there are different premises and different lemmas, and the way in which we combine these to arrive at the shortest proof is also a problem reduction problem. So, let us see how we create a formulation of the problem reduction search problem. So, we will have an AND OR graph where an OR node represents a choice between possible decompositions. So, there can be more than one decomposition, and we will use an OR node to choose between possible decompositions. I will give you an example, concrete example of what I mean by this. And we will have AND nodes which represents a given decomposition, right. So, it means that if you have an OR node, then you have to solve any one of its successors. If you have an AND node, you have to solve all its successors. So, AND nodes are actually the decompositions, and OR nodes will represent the choice between different decompositions. We will come to examples which will clarify this, and later on we will study game trees, where we will, instead of AND and OR, we will have max and min nodes, where max nodes will represent the choice of my opponent and min nodes will represent my choice. So, when we come to game trees, I will elaborate upon this, but these two formulations have a similarity in the sense that both have two different kinds of nodes. Each node has a kind of optimization criterion, like max nodes will maximize, min nodes will minimize, AND nodes will take the sum of the cost, OR nodes will take again the minimum of the cost, if we are looking at a minimization problem. So, this is the AND OR graph search problem. We are given a implicitly specified AND OR graph, where the start node of the AND OR graph, S is the start node of the AND OR graph, T is a set of terminal nodes, and H is a heuristic function that estimates the cost of solving the subproblem at n, and we are to find a minimum cost solution tree. Let me give an example first, and then we will go into the actual algorithm for doing this. So, while I give this example, I will also give you an outline of how we plan to solve such problems. So, first let us understand what do we mean by an AND node and an OR node. So, suppose we start with a problem that we have to solve. Let us say this is something like the matrix multiplication problem. So, I have to multiply matrices A1, A2, A3, right. So, initially let us say that I have an OR node which will say that I want to solve this as A1, A2, A3, and this one says I will solve it as A1, A2 and A3. Now, clear that these are two ways of solving the problem. in order to solve it with this way, I have an AND node which says that you have to solve A1 and you have to solve A2 A3. So, this is an AND node, and here also I will have the decomposition A1 A2 and A3. So, this is an AND node, right. Okay. Now, the way I am going to evaluate it is that I will find out. So, in order to solve this, again I have to take the product of A2 and A3, right. What is the cost of taking this product? Let us put some put the dimensions of these. So, let us say that the dimension of A is 3 cross 4, dimension of A2 is 4 cross 10, and A3 is 10 cross 1, right. So, if that is the case, what is the cost of this A2 A3? 4 into 10 into 1, so that is 40. So, I associate a cost of 40 with this, and what is the cost of this? 0. There is nothing to multiply here. So, this is 0, right. What is the dimension of this A2 A3? 4 cross 1, and the dimension of this is 3 cross 4, right. So, since I have to solve both of these, so therefore, what do I have as the cost of this operation? This particular operation will have a cost of 3 into 4 into 1, so 12, plus the cost of that I have from this, so plus 40. So, this comes to 52, right. Likewise, if you look at this, what is the cost of this? 3 into 4 into 10, so right, and this has a cost of this has a dimension of 3 cross 10, right, and what is the cost of this? 0. Okay. What is the cost of taking this product? 3 into 10 into 1, so 30, plus this 120. So, this comes to 150. In a OR node, I will be choosing, because this is a minimization problem, I will be choosing the least cost successor. So, I will be choosing this one, right, and therefore, finally, what is my solution? It is the subtree that is rooted along the solution if I take the arcs along the selected arcs along the OR nodes. So, it means that this is the way to solve the problem. First take the product of A2 and A3 and then take its product with A1, that is going to give you a total cost of 52, which is the best that you can do for this particular problem instance, right. If you had many more matrices, then this tree would go deeper and you will have more OR nodes and more AND nodes, but in AND nodes the cost of taking this product and this product will add up, plus the cost of taking the product of this and this will be added to that, right. So, that is the cost of the AND nodes. In the OR node, I will select only the best among the successors, and the cost of that best successor will be backed up as the cost of the OR node, right. Now, all this that we have said so far is in the absence of heuristic functions, in the absence of heuristic functions. Just like we had in state space search, we can also have heuristic functions that, given a particular subproblem, gives us an estimate of the best way to solve that problem. It gives us the least cost by which we can solve that problem. Again we can have overestimates, again we can have underestimates. So, at this point of time we will assume that we have only underestimates, right. So, if we take heuristics into account, let us see what happens. So, let us say that we start again with another example, where at the top node we have h is equal to 7, and let us say that this is an AND node, this is an AND node. So, the way in which we will solve this problem is that we will, just like we were maintaining open for state space search, we will maintain a marked AND/OR graph indicating which is the best way of solving the problem up to now. So, if we have an AND node, in order to solve it, we will have to solve both of its successors. So, we simply expand the AND node and we get its successors. So, in this case, let us say that we have two successors, and then again we evaluate the heuristic function in the child nodes. So, let us say that this gives us h equal to 4 and this gives us h equal to 3, right. And in general we can associate some costs with the edges also. These costs will be the costs of merging these sub problems back into the original problem. Like for example, in that case this was the cost of the multiplying of the sub products, right. So, in general we can have separate costs for the separate edges, right. So, now you see what do we have here. We have two successors. This one has an estimate of 4. So, it means that in order to solve this sub problem, we are estimating that at least 4 units of cost will have to be incurred. To solve this, at least 3 units of cost have to be incurred, and because this is an AND node, we have to mark both the successors because both have to be solved. The marked ones are the ones that we will eventually want to solve, the ones that we eventually want to solve. So, now we can revise this cost, because now the cost has grown, because we know to solve this we require 4 plus 2 6, and from this side we have 3 plus 1 4. So, a total of 10 is the new cost that I associate with this AND node, right. And this 10 is also an underestimate, because this one will require at least 4, this one will require at least 3, and if I add up these costs, then the total is at least 10. Is it clear how I arrived at this figure 10? 4 plus 2 plus 3 plus 1. Then let us say I expand. Now, see, when I have this marked subtree, it does not matter whether I expand this first or this first, because for the AND node I will have to solve both, right. So, let us say I pick up this one and I expand that, and this let us say is an OR node. So, we discovered that it is an OR node, and now it has two successors, right, and as we keep on expanding this, we will go to sub problems and sub problems and sub problems, and finally we will arrive at a leaf level where those sub problems are unit level problems which we can solve, right. That is the end of the decomposition, the basic units of problems that we will solve. Let us say here that these two that we have arrived at are the basic sub problems, right, and let us say that solving this requires 9, solving this requires 7, and let us say that these two are 0, right. So, I have 9 here and 7 here, okay. Now, because this is an OR node, I can solve either this or this, right. So, I will choose the one which has lesser cost, right. So, I will choose this one and mark this successor, right. Now, this cost is going to get updated. So, what happens is I am performing a cost revision bottom up. So, I update this one to what 7, right, and then again update this one because this cost has changed. So, this will also change, So, now this is going to be 6 plus 8, so 14. So, this one gets updated to 14. So, as of now I can see that this is the best way of solving the problem up to this part, that this is the best way of solving it, but I have still not solved this one. So, I will expand this, node, and let us say that this is also a OR node. So, I will expand that, and let us say that I get 2 nodes. This one has h equal to 5, this one has h equal to 2, right, h equal to 5, h equal to 2. So, you can use pathmax if you want. Where is heuristic less than that of it? Here. Yes, yes. So, you can update it if you want, right. So, if you can update it if you want using pathmax as we had done previously, right. So, let us go on with this example, and those optimizations that you can update this, we can do it later. So, let us say that this one has a cost of 1, this also has a cost of 1, right. Now, see, heuristic of this, suppose this had cost of 2, then you have nothing to worry about, because this is 2 plus 2 4, which agrees with this, right. It is because 2 plus 1 is 3 and that is less than this, right. So, if you want, we can make this 2 also, let us make it 2, right. So, now if we compare this, this has a cost of 4 and this has a cost of 6. So, therefore, we will mark this one as the best successor. In an OR node, we always mark the best successor, the current best successor. Now, if we mark this, then this cost has not changed anymore, this cost has not changed. So, therefore, we do not have to do any cost revision beyond this point, because this cost has not changed. So, there is no need to go further up, this cost will still remain as 14, right. And now, let us see what is the best solution that we have. We solve this here and this here, right. So, now again we want to expand another node. Now, which node will we select? This one. So, we are not selecting this node for expansion, because currently this is not good, this is better. The OR node has picked this as the successor. So, we are always going to pick up a leaf node of the marked subtree. So, in this case, the marked subtree so far is this. So, we will pick up always a leaf node of the marked subtree and expand that. So, in the marked subtree we have this one. So, we expand this, and this gives us again, let us say we have 2 successor, one has h equal to 3, right, and the other successor is a solved node which has 10, this is 0, this is 1, let us say, and this is an AND node, right. So, now what is the cost? This cost is going to get updated, it is going to be how much? 10 plus 0 and 3 plus 1 4. So, 14, right. Now, this cost has changed, by the way, because this is the AND node, both of its successors will be marked. Now, we take this node, and again because this cost has changed, this whole cost revision step will have to be done. So, now this one will get replaced by 16, 14 plus 2, 16, right. Wait. Now at this point of time we have to see which is the best cost successor of this OR node, right. Now, if you look from this side, what you are getting up, what is being backed up is 16, but from this side we now have a better one, that is 6. So, we are going to choose the less of the two and take 6 as the heuristic cost of this node, right. Now, does that change this? It does, because it has changed from 4 to 6. So, this is now going to become 16. Is this clear? And now, the marked successor is this mark is not there anymore. This mark has shifted in this direction, right. So, the mark shifts when I find a better successor of the OR node. So, the mark has shifted here, right. Then I expand this, and let us say I get this, let us say that this is an AND node, and I have this with a cost of 3 and this has a cost of 4, and they are all solved nodes, terminal nodes. So, now what is going to happen? This is going to get updated to 7, right. Now, this is going to get updated to 8, but this is still the best successor. This is still the best successor, because we are comparing between 7 plus 1 and 14 plus 2. So, between 16 and 8. So, we will select this one still. This is going to get updated to 8 and this is going to get updated to 18, right. And now we are in a point where all the leaf nodes of the marked tree are solved. So, the best way to solve this problem is by following the marked tree and solving those problems. So, what we are going to do is we are going to solve this problem, we are going to solve this problem, then we are going to solve this, then we are going to solve this, then we will solve this, that will solve this, and then we will solve this one, right. And the best cost of solving this is going to be 18. Is it clear? Is that all right?
So, but we haven't solved the other one, right? The first one.
Yes. Coming back to here, you are saying that we haven't yet solved this one.
Yeah, we haven't gone ahead with that.
Yes, but see, our heuristics are underestimates, right. So, this one is going to cost at least 16, if not more. So, if you go further down, your cost can only increase, because the heuristic costs are underestimates, whereas on this side you have actually got a solution of cost 8, right, a complete solution of cost 8 for this one, and in this side it says it is at least 16. So, between at least 16 and exactly 8, we know that exactly 8 is always going to be better, right. So, we do not actually go to solve these things any further. So, the full AND OR graph is not going to be explicitly generated. This is progressively expanding it best first, only up to the point where we have got the minimum cost solution. Right. Now, if you think that we could have solved A star also in the same way, we could have taken the initial problem, except that in A star we do not have AND nodes, we only have OR nodes. To solve the start problem, there are several different choices in A star, the set of successors, and then take the successors of those successors, and in this way you could expand it out into an OR graph, right, a graph which has only OR nodes, right. And we could use the same marking strategy, always maintain the best cost successor at every OR node, right. Now, if we did that, then we will still arrive at the same solution as A star does. At every point of time, the node that you are selecting for expansion will be the node that is along the best cost path from the start state. That is the minimum cost node that we are always expanding. right. So, that will be the only node which is along the marked path. Because we do not have AND nodes, there will be only one marked path from the start state, is not it? So, try to think of A star in the context of AND OR graph search. It actually is doing the same thing as well, but there we were maintaining open as a separate list. But if you think of open and closed together, it is nothing but this tree, right. So, now let us look at the algorithm that we just now worked out. So, initially we will define a thing called G star. Now, G star here is the marked subtree rooted at the start state. At every point of time it will denote the subgraph which has so far been generated out and rooted at the state space. And initially the estimate of the cost at the start state is equal to Hs, because we do not have any other cost at that point of time. Now, if we find that the start state itself is a state belonging to T, T is the set of terminal states. Terminal states represents those subproblems which are unit level subproblems, which we do not further decompose but solve directly. So, T is the set of subproblems which are directly solvable. So, if we find that S belongs to T, then we will label S as solved. Whichever is a terminal node can be labeled as solved. Then if at any point of time the start state is labeled as solved, then we terminate, right. Now, when we are in a OR node, right, and the best cost successor is marked solved, then we label the OR node as solved. In an AND node, when all its successors are labeled solved, then we label it as solved. So, we are coming to that. So, the third step is the select step. So, what we do is we select a non-terminal leaf node from the marked subtree, as we were doing previously. At every point of time we just look at the marked subtree and select the non-terminal leaf node. Then expand that node to generate the successors of the state n. For each new successor, we set Fm equal to Hm. For each new successor, mind you, we set Fm equal to Hm. If M is terminal, if any of the successors is a terminal node, then we label it as solved. And then after we have done this, we will call cost revise, which is the bottom up cost revision step, and finally we will return to step 2, right. Now, let us recall the example that we had done just now, where, well, it is all cluttered up here, but if you remember that we had initially started with the AND node, generated its successors, right, expanded the node, generated its successors, then marked for an AND node we mark both of its successors, right, and then for an OR node we mark only the best cost successor, and we label a node as solved only when the best cost successor is labeled solved. So, when this is solved and at this node we find that the best successor is this and the best successor is solved, so we can label this as solved. Then we expanded this node, and initially first time we went this way. When we backed up this cost, when this was the best cost successor, it was not solved. That is why we never labeled that as solved at that point of time. But when we went this way and found that this was solved, and then because this is an AND node, both of its successors are solved, so we label this as solved. Then when we went back to this OR node and found that the best successor is solved, that is when we label this as solved, right. When the best successor is labeled solved, we label it as solved. Why? Yes, because the other along the other directions we will only have more cost, because they are all underestimates, and if this is the better than those underestimates, then this is the best that we can get. So, we label it as solved, and then when this AND node had both of its successors as solved, then we label this as solved. And if you look at the algorithm, whenever S is solved, that is when we terminate. Now, let us look at in details at this step. What do we do in cost revise? What do we do in cost revise? That is where we will compute the costs of the parents from the successors, and in on nodes we will decide to shift the marking if necessary. So, what we are going to do is, we are going to start with the node from where we want to do the cost revision. So, let us say that in this, when we came up here and updated this cost, right, then from here we will do the cost revision backwards. So, initially, which is the node that we generate at the bottom is the one from where we will start the cost revision. So, we found that this is 3 plus 1 4 and 10 plus 0 10, so 14. So, we start cost revision from here, right. Now, what we do here is we create z equal to n. So, we start with z equal to this state n, right. Then coming to the slides. Okay. When z is empty, that is where we are done. Otherwise, select a node m from z such that m has no descendants in z, right. Why do we do that? Because we want to go bottom up. So, we will always select first the state which has no descendants in z. Then, if m is an AND node with successors R1 through Rk, then we set Fm to be the sum of the child nodes plus the cost on the edges, right. So, this is Fri plus Cm Ri, which is the cost of the successor Ri plus the cost of the transition from M to Ri, cost of the edge from M to Ri, and then we sum it over all the edges. That is because this is an AND node, so we have to sum it over all the edges, and then mark the edge to each successor of M. Because it is an AND node, we mark the edge to every successor, and if each successor is labeled solved, then label M as solved, right. Okay. After this, what we need to do is, we have to check whether after this exercise the cost of M has changed. If cost of M has changed, we will put it back into Z, so that in the next iteration or subsequent iterations, we also examine whether the parent of M is also going to change, right. Okay. What happens if M is a OR node? If M is a OR node with successors R1 through Rk, then similarly we compute the cost of solving every child as Fri plus Cm Ri, but because this is a OR node, we will find out the minimum among these. And that is going to be the new cost of M. So, cost of the OR node is the minimum of the cost of solving its successors, and then we mark the edge to the best successor of M, and if the marked successor is labeled solved, then we label the OR node as solved. Agreed? And then finally, if the cost of M has changed, regardless of whether M was a OR node or AND node, if the cost or label of M has changed, then insert the parents of M into Z for which m is a marked successor. Now you might find something interesting here. We are talking about insert those parents of m into Z. Now when we are talking about AND OR trees, as we have done here so far, there can be only one parent, right? But in case you have a graph, AND OR graph, then you can have more than one parent. At this point of time we are not talking about graphs. If you are further interested in this area, you can read up what happens in the case of AND OR graphs. Okay. In any case, any graph can be unfolded into a tree. So if you do not want to remember whether you are visiting the same node from two different paths, you can treat that as a AND OR tree. Is that all right?
So why don't we just climb up the tree and just update all of them instead of maintaining Z?
Okay. So the question is, why don't we just climb up the tree and update all of them as they are along that path, right? Now that is essentially what we are doing also. What we are doing is, in the case of a tree, because there is only one parent, we can just, what will happen is, it is you will have always n will have a single parent. So if the cost of n changes, then the parent of Z will be put in Z, and then in the next iteration the parent will be picked up, right? And if the parent of that parent gets changed, then that is the one which is going to get inserted. So it's the same thing that's happening. But in the case of a graph, suppose you have the state n, and this state n could have been the OR successor of some node, and could have been the AND successor of some node, right, or could have been the OR successors of two nodes also. So in that case, you see, when the cost of n changes, the cost of this node can also change, the cost of this node can also change, right. Okay. So as a result, we will put this also into Z, we will put this into Z, and we will also put this into Z, right. So that both of them are again updated with respect to their respective parents, right. So because this algorithm that I have talked about is for AND OR graphs in general, though the example that I have given is for AND OR trees, but this algorithm itself is applicable to AND OR graphs as well. So therefore the cost revision steps that we have mentioned here are actually meant for graphs.
But in the algo, the 6th point is that insert only for which m is a marked successor.
Yes.
So
Yes.
m is a marked successor for only one parent, not for all the parents.
No. It can be, see, look at this example. In this OR node, the best way to solve this OR node could be this, and in this AND node, both of these are marked. So it's also the marked successor of this, and as well the marked successor of this.
Sir, if it is marked, if it is not marked for AND, then it will not.
No, see, if it is not marked, suppose this OR node is actually pointing in this direction. So it is not selecting this. So this option for this OR node, this option is still better, right. So therefore this cost is going to come up from this side, it is not going to come up from this side, right. So if there is, if the parent node is still marked the other way, then you need not do cost revision beyond that point, right. If this fellow's cost changes and the mark shifts from here to here, then we need to put this back into Z, so that this fellow's parent also gets the chance to see whether now this becomes the better path. Understood? Is that clear? Any questions regarding this algorithm? No? Right. What I would suggest is, you take a few more examples by hand, by graph AND OR graphs, right, and try to see how best to how you can apply this algorithm by hand to solve it. Yes.
If the node is marked solved,
Mhm.
does it signify?
If a node is marked as solved, it means that you have already found out the best way to solve that subproblem. So, for example, if in an AND node recursively, if an AND node all of your successors are solved, then you have solved that AND node, because you know exactly how to solve everything from below that AND node. In an OR node, if the currently selected successor is labeled as solved, then you know that you need not worry about the other successors, because those other successors are going to cost you more. So, the marked successor, if that is labeled as solved, then you know that if I follow along this mark, then I have already solved everything below that. So, I can label that node as solved. What are the initial set of solved nodes? The terminal nodes. The basic subproblems which cannot be further decomposed are the initial set of solved nodes. There is a fixed cost associated with each of those terminal nodes. So, that is the cost that you have to incur that unit subproblem, which cannot be further decomposed. Okay. So, a class. So, how does AO star fare? So, this algorithm that we had so far is called AO star. It is the AND/OR graph search algorithm. So, we call it AO star, AND/OR star. How does it fare when the graph has only OR nodes? Well, it fares exactly like we have in A star, right. So, the next topic that we will look at is searching of game trees. I will not start this topic today, because we are nearly towards the end of this lecture. So, I will not start this topic. What we are going to see in game trees is we will have two types of nodes, just like we have AND nodes and OR nodes. We will have max nodes and min nodes, and we will see how we can model a game playing problem as a problem of solving game trees with max nodes and min nodes, right. So, the next lecture will talk about game trees and how we solve game trees, right, and I also intend to wrap up a little of the previous things that we left on search, so that from the next to next lecture we can get started with knowledge and deduction. Okay. So, in today's class we will start on game trees, and we will see how we can model different game playing situations in terms of game trees, and we will study some very classical algorithms for searching in game trees and finding out when we are in a better position and when we are in a worse position. So, in this on searching game trees, what essentially game trees are, they are OR trees. Namely, we have already studied what AND/OR graphs are and AND/OR trees are. So, game trees are a special type of OR tree, but there are two types of OR nodes. By OR tree we mean that at a time we will be selecting only one of the successors of the OR node, but which one will be selected will depend on whether it is a min node or a max node. I will shortly explain why we need this kind of a representation. And briefly, we in min nodes we will select the minimum cost successor, and in max nodes we will select the maximum cost successor. Terminal nodes can be winning or losing states, but it is often infeasible to search up to the terminal nodes. So, we will use heuristic cost to compare non-terminal nodes. So, let me start by showing a simple formulation of a game tree search problem. So, let us say we take the example of tic-tac-toe. So, in tic-tac-toe what we have is something like this, right, and the players alternate in putting either a circle or a cross in any of these positions. So, let us say that we start with a configuration where we put x here, right. Then from here, so this is where the this is the starting configuration, let us say. Now, it is the move of player B. So, when it is the move of player B, then there are various different moves that player B can take, say out of which this is one, or this is one, and so on. Then for each of these cases, player A has a move. So, here let us say player B has a move from this point. In each of these states, player A has a move. So, suppose player A makes a move here, then player A can again take one of many different moves. So, suppose if this is the state, then player B can give something like this, or player B can give something like this, and so on, right. Then you know that suppose this is the move that player B has given, then again player A will have turns, but if you look further below this, then you will see that there is a way of playing by which this fellow always wins, because if now the only possible option of this player is to put a dot here, and if that happens, then the other player can put a cross here, and then there is no way of saving the game, right. So, if you look below this subtree, then you will see that for every move that this player makes, the other player has a winning strategy, right. So, now this is the structure of the game tree. The game tree is a tree where every node of the tree represents a state of the game, and nodes can be either a max node or a min node. I have not yet defined what I mean by a max node or a min node, but let us say that one of these types of nodes is for player A and the other is for player B. So, depending on who has the move, we will distinguish between two types of nodes, right.